Hi, I'm Narayan Desai, and I'm going to be talking about Goldilocks reliability and how we can do better. This talk actually has some seeds for this talk were planted in conversations after the last SREcon, and for this reason, I thought it would be useful to start this off in a little bit of a different way than the way the talks normally start. I'm just going to start up front with the acknowledgements. So the ideas that I'm talking about in this talk are based on the work and discussions and contributions and critique of lots of people. In particular, the methods and some of the failings of our existing models have all been developed by the Kraken team, my team at Google, working in conjunction with partners across a variety of service teams who have raised the particular problems that they struggle with, and pushed us for rigor in what we're doing. The broader issues have really benefited from discussions with a variety of other folks in Google and around the community. So at a high level, what we're trying to accomplish here is to build a better approach for understanding the reliability that our services have. So there's three things that we really want out of this process. The first is we want a good map to understand what the reliability of our service is, where the problems are, and where we should really be investing, right? We all have limited amounts of time that we can spend. And you can spend that time well or poorly, right? In terms of problems that will or won't happen. There's always just more work to do than we can possibly accomplish in the time that we have. Along those lines, one of the things that we also think is very important is building tools that work on the basis of automated reasoning processes to speed up the way that engineers engage with problems, right? So, really this is about scaling sublinearly. Now, the third component that we really care about a lot here is trying to figure out the underlying dynamics of our systems from a reliability perspective, right? What are the underlying mechanisms, the reliability mechanisms that exist in our services, and how do they interact with one another, and how do they add up to either stable or unstable services? So with that backdrop, on to Goldilocks reliability. So I'll start with the story of Goldilocks. So this is a fairy tale that many of you are probably familiar with. The basic story is three bears live in the woods. They have made themselves some breakfast, but it's too hot, so they go out for a walk. And while they're out, a little hungry girl comes in and sees the food on the table and starts sampling it. And this story is usually used to teach children about the notion of just right. So, the first bowl of porridge is too cold, and then the next one is, the first one is too hot, and then the second one is too cold, and the third one is just right. And so, this sort of has this implicit notion that everything in the world can be lined up, in terms of these various characteristics from, too much to too little, and then there is some sort of sweet spot in the middle. And we use the phrase sweet spot all the time to talk about this kind of stuff. So in the reliability context, I'd argue actually that this is the general approach that we use to understand the reliability of our services in a lot of cases, right? So this typically has, three steps, right? The first one is choose some SLIs. So these can be, real number or integer numbered things, data from our services having to do with the performance, latency, throughput, failure rate, whatever. And then through a relatively simple set of methods, we choose just right. And so this usually requires an expert to look at the data and figure out what reasonable operational ranges for these metrics are and when things would be out of bounds. And this is used for us to distinguish between cases that are expected and cases that are unexpected. Right, and then, step three is roughly profit, right? This is a really simple analytical model. Everybody can understand it. The math behind it is relatively straightforward, so that it's pretty accessible, and the assumption here is that clarity ensues. We also see that hilarity often ensues because it turns out that the behavior of all of these things is kind of complicated. Now, you might recognize this approach from the vast majority of techniques that we use to understand reliability of our services today, right? This is how monitoring works. This is how SLOs work, and that that results in all kinds of problems. So, so I'm going to move to this quote. I think that this is a really useful idea to keep in mind. So this is a quote from a statistician, George Box. All models are wrong, but some are useful. And I was chatting about this recently with Lauren Hochstein, and he added on, and some are dangerous. And I think this is really roughly correct. We need to treat all of these things with some amount of suspicion, because these models don't represent truth. They represent some aspect of the situation, and they have a useful operational range, and sometimes they will give you good answers, and sometimes they'll give you bad answers. And so, the first message of this talk is to be skeptical about these models a little bit and treat them carefully, because just as often as hopefully not just as often, but they can often give you insights that are incorrect. And this is really problematic. So in order to understand where this Goldilocks model can lead us astray, we really need to think about how this model is constructed. And a great place to start there is what the assumptions are in the architecture that are load-bearing. So in the case of sort of Goldilocks reliability methods, there are four major components here that are pretty important. So the first one is that the notion of just right makes sense, right? So this is the notion that the metric that you're measuring can be lined up and there is an operating range where you expect it to be. So this is true in some cases and it's not true in others. But the Goldilocks methods only really work for metrics that are structured this way. And there is nothing that necessarily makes metrics structured this way. You could imagine, for example, the runtime of a Unix executable as a metric. It may be short, it may be long, right? It's really hard to actually say what just right is for that kind of a metric. So the second assumption that we make here is that there is one answer, right? So the idea that you could choose just right one time and end up with something that makes sense. Now, even in cases where these metrics are properly distributed, you can run into problems where you're aggregating lots of different kinds of things together. And in that case, then what you end up with is aggregations that don't necessarily have predictable properties, and that makes it very hard to discern whether things are working or not, right? Now, as you start to aggregate more and more pieces of workload together, for example, or different customers or whatever, this isn't necessarily true, and that can lead to problems. A third aspect of this that's pretty important is that, the idea of these Goldilocks methods as a sort of a comprehensive view of reliability is predicated on the idea that we know what we need to know. So each of these measures are narrow, and they don't typically tell you anything beyond a very particular notion of how a service is working at any given point in time. And because of that, you need to use lots of these measures. And then the last assumption that we make here is that these answers aren't going to change very often, right? So when you have these patterns of behavior, then you end up with lots of complications when things change. So these measures are really, really sensitive to these calibrated thresholds being chosen properly. And when they're not, this basically causes noise in your analytics, and you end up with conclusions that you probably can't trust very much. So how does this really cause us trouble? Well, to start with, this doesn't really codify any model of reliability, right? Like, this is just a way of describing whether a metric fits within an expected range or not. And that's actually kind of problematic. This isn't going to tell you, this doesn't encode any other expectations of behavior or anything like that. And this really results in a complicated analytical machine because everything is tuned just so. Moreover, it's brittle, right? Because it can't really be configured in a particularly principled way, and you don't know when you're going to run into problems, fundamentally. The second thing is it's actually really hard in many cases to figure out what just right is. Due to the reasons that I mentioned earlier, right? If you end up with metrics that aren't structured, that don't have the right sort of natural distributions, or if you're aggregating too many different things together, it can actually be really hard to see. The mean, for example, of the runtime of Unix processes on your laptop is not going to tell you much, right? The third thing is each of these provides a very narrow window into behavior, and this really causes two different problems, right? The first one is you don't know what you don't know. So you frequently see this pattern in services, even as they get very mature, that you need to add additional metrics over time to understand what's going on as you find new classes of outages. And moreover, you don't know where you are in the process, right? Like, you don't have a sense of if you've got 20% coverage or 80% coverage. And this is a problem, right? This is what leads to most teams being in a situation where they have perennial work to do to maintain their monitoring configurations and their SLOs, but on a really sort of unpredictable cadence. And lastly, we don't know how to do a reasonable maintenance cycle for this calibration. These shifts can happen for lots of different reasons. Imagine if, for example, a library that you consume gets faster. You are in this situation where, maybe you should actually change all of your thresholds, because slow is no longer, acceptably slow is no longer acceptably slow, and everything should be, n milliseconds faster. And we don't really have a robust way to understand when things are going to change and how often we should be spending time here. So all of these are issues, right? And I think it's worth really drilling into this issue with thresholds in particular. So if you look at this analytically, this picture on the left, it's a visualization of a particular metric. So this is a real numbered metric. It doesn't really matter what it is, but it's relatively rich. We have lots of points. This is on a log scale. So we've got distributions in there and lots of other juicy things that we can use to figure out what's going on. Now, if you think about what happens when you map this through a threshold, is that the data product that you're left with is this one on the right. And this is a 2-bucket histogram, and 2-bucket histograms contain a whole lot less data, right? Specifically, this 2-bucket histogram contains 2 64-bit integers versus a large number of data points. And this represents a really substantial loss of fidelity from the data product on the left. Moreover, if you've chosen the threshold incorrectly, it's not just a profound loss of data compared to the data product on the left, but it's a complete loss of data, right? So if you're, as a thought experiment, if your threshold was a factor of 10 higher than it should be, then you need to figure out how to, you can't see anything anymore, right? Like, if one of those buckets is smaller than it should be, or 0, like, you have a problem. And so this is the kind of behavior across the board that typifies these Goldilocks processes, right? If it's calibrated properly, you can see some things. If it's not, you really have problems. Okay, and so there's additional structural problems that we have here. Like I was just describing, calibration implications are incredibly high stakes. There's, making these decisions incorrectly means that you go from potentially being able to see problems to not. We need to make lots and lots and lots of decisions because all of these metrics are narrow, and so that means that we're constantly deciding new thresholds to make here to reason about our services. And it's also worth mentioning here, people make mistakes, right? So there have been studies that have documented errors in repetitive processes, right? People make, more upwards of 10 errors per 100 decisions. This is potentially a huge problem, right? Moreover, we don't actually have a metric to judge quality, never mind quality control process. Another sort of orthogonal point is that we don't really, this model doesn't do us any favors in terms of understanding what's going on. So it tells us about the behavior of a single metric. And we can't abstract, right? So we can't step back and draw broader insights from these things because they're very noisy data products. And the other thing that is really problematic is there are also lots of social pressures that cause us to detune these things, right? So, for example, a team might set its SLO higher than they could from a strict performance perspective because they can only deal with so many pages, or they can only deal with so many incidents or alerts or so forth, right? And so this causes these analytical methods to be relatively detuned. And as they're detuned, we can't see the things that we need to see, right? So this is really a big issue, I think, particularly for understanding reliability from a mechanistic perspective. And I think the thing that bothers me the most about this process is that it's really tempting to look at this as process failures, right? Like, if only we worked harder at it and we spent more time on it, we could build these processes in a way that would work a whole lot better. And I think this is really rough, because fundamentally, this system isn't doing us any favors, right? And so we need to do better here, right? I think, in the spirit of not feeding the machine with the blood of humans, that's what these processes do today, right? We just sort of heap more and more load on people to make better quality decisions more often and spend lots of work trying to figure out what's going on our services. And meanwhile, it's not really serving us very well. So we need to think about other approaches. So I think if I had stopped the talk here, you'd probably all be pretty irritated at me. So we have some ideas for things that we can do that are better. And so that's what I'll talk about from here on out. So I think before we talk about anything else, I think it's worth actually defining, at least for the rest of this talk, what we mean by reliability. Because I think we also suffer from a lack of concise terms. And because of that, it's actually really hard to communicate effectively about a lot of these more complicated things. So when I'm talking about reliability throughout this talk, I'm really talking about three things. So these will all be familiar concepts, but effectively, users care about availability, right? That when they make a request of a service, it's there to answer and it can function properly. That the service performs in an effective fashion, whether you're considering, for example, the latency of a request, or you're looking at the cost per byte, or whatever, right? Users care about that quite a bit. And then the third part is that the service does what it's supposed to do fundamentally, right? That it's correct, that it doesn't have horrendous bugs in it, and so forth, right? Now, it's worth noting that for reliability, we have all gotten in the habit of measuring it from our perspective, but I think fundamentally it's actually more important to measure this from the perspective of the users of our service, right? At the end of the day, they're the ones that get to decide whether our service is reliable or not. And so, as we think about these aspects of service reliability, it's really important that we think about these from a user's perspective, because if we don't, we can get tricked into using narrower measures of things than the end-to-end properties that customers care about. Okay, so now that we have a definition, we can start to think about models, right? And so, taking these quotes to heart, I think that there's roughly three things that we need here, right? So we need models that we can accept are wrong, but they need to have useful properties. And we need to make sure that they're not dangerous, right? That we're starting to really avoid some of these pitfalls that I was describing earlier. So let's think about reliability. Oh, so sorry. So I think the thing that we need to do here at a high level is make more models, and what this ends up looking like is roughly three stages. So the first stage is you need to mathematize your intuition. So I think that SRE and the operations field more broadly has done an incredible job of training up a really keen intuition, right? After you've been on call for a service for a while, you know how it acts normally. You sort of get hunches about what things look right and don't look right, and so forth. And so the first step in figuring out one of these models is to specify a behavior that you think is true or should remain true or is mainly true or that you want to understand, and come up with some way to describe it quantitatively. Right? Okay, so if, once you've done that, the second step is to backtest and refine. And so what you can do is take data and see what your model says, and check if the model says something that agrees with the experiences that you've had. And I think that the overall situation here is your model's not going to be right. None of these models are right. It's really important to understand how well they do work and if they tell you useful things or not. And you're going to need to do this multiple times. So for example, the model that I'm going to describe later in the talk, it's not our first model. The first model we abandoned because it didn't tell us things that were useful. So this is part of the process, right? I think iteration is really key. And then the third thing is, understand and share, right? Because I think we all want to understand our services better, and these methods will undoubtedly be applicable across systems. So now when you think about models, I think one of the things that's important is that you're going to need lots of different models to cover different sorts of things, right? So you might start with a very simple model describing a roughly spherical elephant. And then you might add on an additional model in the bizarre situation that an elephant is water skiing. Or you might need to know how an elephant tail functions or how its ears flap, and that's going to be different. Or you might need to know, what causes its skin to wrinkle, or how fast it blinks. Or you might want to understand how its tail bends, right? All of the, or not its tail, its trunk bends. All of these things are going to be different, and roughly these will all correspond to different models that'll tell you narrow aspects of particular behaviors of your service. And it's important to start to create these, and you're going to see different kinds of models that are appropriate in different situations, right? So you might want to use, we're using statistical models, for example. You might want to use statistical models because, that corresponds to the kind of process that you're looking at. Or you might want to model, cascades using networks, and those will be completely different kinds of models. Certain sorts of things, cascades might start with first passage type processes. And so maybe you need to couple multiple types of models together. Over time, we're going to build more of these models, and they will illuminate how different aspects of our services work. And I hope that these can be generic. We've got some cases that suggest that they are sometimes, and hopefully we can build lots of generic models that will tell us useful things about how our services behave under load. So let's go through this playbook. We need to take we need to build a model. We need to take some intuition, figure out how to describe it mathematically, and then see what we can use it for and if it's a useful model or not. So we developed a model, and let's start with the property that we're looking for here. If you think about availability from the perspective of stationarity, right? So stationarity is the property that the distribution remains fixed over time. So if you think about what a user expects of a service, stationarity is actually a really good fit for it, right? Because they really want a service that was the same yesterday as it is today as it will be tomorrow, right? So that's a really easy thing to understand. They don't need to actually get deep into the nitty-gritty of you can expect up to this many errors over this kind of a window that replenishes at this rate, and so forth. We've come up with complicated ways to bound performance, and instead, this is a very intuitive thing for a user to understand. So if you consider availability, really what you want to say is that errors are IID right? Independent and identically distributed across time and space and customers and workloads and all that sort of stuff. If you think about what this means for performance, this means that performance sort of draws from a stationary distribution across time, right? So that means that if you think about the distribution of performance that you get for a particular workload over the course of a couple of days, it should be the same over the next couple of days. And for correctness, really what you want is the service to produce the same result over time, modulo bugs. And this is really an intuition about what it is this is a phrasing of what our goal should be. Now, we know, for example, that all of our services are not stationary in this manner today. But what we are hypothesizing is that measuring stationarity is in fact a useful thing to do, right? Because if we measure stationarity, we can assess roughly how far we are from the intuitive expectations of our customers. If you think about that in terms of availability, that means how often they're seeing errors. If you think about that in terms of performance, that means how fast or expensive are their workloads. And if you think about that in terms of correctness, you just want to make sure that they're getting the same thing over time. So the good news here is that stationarity works. So we've built a method, and I'm not going to go into too much detail for how it works, because that would take considerably longer than I have. But the basic approach is to assess the relative likelihood of a particular event, right? So if you think about a workload as consisting of lots of requests that each result in work, if you take, for example, a performance measure, you can sort of rate that in terms of how likely that particular outcome is. And then we just look at a windowed average of this over time. And what you can see in this graph is a situation in which the service ended up getting slightly under provisioned, and then it started behaving badly. And this performance started to occur, and at this point we didn't have the real-time analysis up and running yet. But we started to see problems. A little bit later, customers started to notice problems themselves, and then eventually they escalated these problems to us. Now, the thing that's really interesting here is the x-axis. So we were really surprised to see, how these things build up over time, and this opens the door to a bunch of really interesting questions, right? If you think about the way that our teams are structured and function today, almost all of our interventions are acute reactive interventions, right? You page someone and then they go do a thing because the service is really experiencing a problem right now and it needs to be fixed right now. However, you start to look at these problems that start to exist in higher sensitivity metrics where they begin to boil over the course of days. This is suddenly a task that you could engage in proactively with your morning coffee, right? On the morning of the 13th, someone could have, looked at performance variation, spotted this sort of issue, and then resolved it before it got worse. And so we're really excited about this. This method, just a few more details about it. So it's calibration free. This means that you don't need any human judgment in the process. It works on the basis of historical data, and the fact that it's calibration free is also important. Like, we can say empirically, once you're starting to see these rates of really unlikely events clustered together, that something really bad is happening. So another thing that we have built on top of this same kind of an approach is applying the same analysis to multiple kinds of metrics in a hierarchical structure. And so the general idea here is that you are able to score the likelihood of end-to-end latency spans, but also score the likelihood of subspans. And then you can use this to sort of navigate the hierarchical tree to understand which subsystem is causing your problems. So what this graph shows is a period where the IO subsystem in a particular cluster was in distress for a couple of days. That red line represents a square wave that of all slow events, 100% of them had extremely slow IO times. This becomes a really easy diagnostic tool. which can even be interpreted relatively quickly by a non-expert in the service. And so this is an example of the kind of tool that I'm talking about when I talk about building better tools, right? As opposed to a manual diagnostic process where a person who maybe isn't so familiar with the I/O subsystem of the service has to go and diagnose this and figure out where the logs are and figure out where the metrics are and then try to figure out how to interpret the metrics. This is a really unambiguous signal that something is going on and that this is a pervasive problem. Moreover, this is, when you see these rates, it's also clear this is not a problem that is rooted at the workload, which is a really interesting property. So at a high level, what we've ended up with is this very, very sensitive measure of system behavior using an underlying model of reliability. And with this, we've been able to see a lot of things that we knew existed, but hadn't been able to directly observe before. So for example, we can see subcritical performance shifts. So, typically you think about alerting and SLOs, looking at the tail of the distribution, right? P99 or P99.99 or whatever. We can see performance shifts at P50, things like that. The sensitivity is considerably higher. We're also able to see these longer running, slow building reliability incidents, and particularly performance incidents that cascade into availability incidents. We're able to see performance regressions caused by new releases or misconfigurations. We can route down to subsystems relatively quickly through this diagnostic process. We can see provisioning issues and see the effect that they're having on the service in a really granular way. We've been able to detect correlation problems which indicate isolation failures. And at the end of the day, the thing that's the most interesting about this is that this all corresponds to the intuitive understanding that our users have for what our services should be doing. And so this is a really important aspect of things. So this also opens the door to lots of interesting new things that we're building prototypes of or have built prototypes of. This allows you to start to build impact assessments from first principles that are very, very reliable. We had one example for an incident some time ago where the impact assessment in the postmortem took one of the TLs 12 hours to put together because they needed to come up with the metric, the footprint of metrics that would describe whether a particular request was impacted by this problem that we were having at the time, and they tried to put something together. And despite their best efforts, the assessment that they were able to come up with after 12 hours missed several things that our model was able to find. And as we've gone through and done back testing, we've been able to validate that the model is in fact very reliable. I mentioned proactive reliability interventions. I think this is a really, really big deal because we have just set up so much of the reliability process around these acute interventions. And so the idea of being able to do something proactive on a routine basis opens a lot of doors. Fundamentally, what we're doing today is we're treating all reliability interventions as a trip to the ER. And I, like going to my doctor for an annual physical. I like being able to sort of get these more sensitive assessments of where I am, and I'm not going to go into too much detail, but fundamentally, we don't want everybody going to the ER, and that's what we do today. I think we're starting to be able to measure ambient instability, and that opens up a lot of interesting questions about what the dynamics of our services are. Mechanical diagnostics, again, this is really, really transformative in terms of what we can do with it. And I think this is really getting us towards this situation where we'll be in a position to start to prioritize reliability investments based on the data that we have. And we do this today in a very, very coarse-grained way, but I'm hopeful that we'll be able to start doing this in a much more nuanced subsystem level way, right? Clearly we all prioritize today based on where we've had outages. But it appears that we will be able to build, calibration-free assessments of subsystem stability, which would be able to tell us, what the parts of the system that are most likely to result in problems are, independent of actual outages, which is a really exciting possibility. And again, direct detection of customer pain. This is incredibly important. I know I mentioned it on the last slide, but it's so important I'm going to mention it again. At the end of the day, our ability to build reliable services is measured by the folks that use our services. And so the better that we can understand the experience they're having, the better. Or the more that we can understand, the better. Okay, so in conclusion, I think we need better ways to think about reliability. I presented one model here. I'm not saying that that's the way to do it, but I think this is going to come about through a couple of things. We need concise terminology. We need to be very specific about what it is we're talking about. We need to agree on these definitions. I don't think that we need a standards expedition here, but I do think that we need to really get very precise in what it is we're talking about. And I think we need well-articulated models. And the way that models have typically gone in established sciences is that they've moved, they started from, the perspective of interpretive models, and they've moved towards being predictive models over time. And I think that that's really where we want to go long-term. So what this means is make more models, right? Everybody make models. We need to figure out what the ones that are good are and start to use them more broadly. And try this at home. Talk to your friends. Make models for the problems that you have, and then validate them, right? I didn't really talk in much detail about the validation process that we went through here, but we actually literally spent months on validating this model, because the last thing that you want to do is lead people in the wrong direction. So I think it's actually really important that we figure out exactly how to do all of this stuff. And then at the end of the day, this is going to have to be a collaborative endeavor, right? We need to talk about what we're doing, share what works and doesn't and why, where the corner cases are, and then really all move forward as a community. I think it's really critical to not take anything for granted and be a skeptic. I suspect that won't be a problem for this audience. But be very careful about the things that you trust blindly. I mean, I remember the first time that I was on call for a service and we had a bug in a dashboard, and it was like, my innocence had been lost. We all need this kind of skepticism. So in terms of the specific model, and I'm sorry I didn't have time to talk about it in more detail, Stationarity is a model that is giving us a really effective new lens to figure out what's happening in our services. And it's enabling lots of cool stuff. We can see things that we knew were happening in our services but weren't able to observe. And we're building new tools, and it's helping our engineers to figure out problems that were really, really hard to track down before. And I think that we're starting to gain some useful insights into the underlying dynamics of the system, which, as you start to develop these more precise, higher fidelity metrics, you can start to see more things and understand more of what's going on. So this, a lot of what I'm talking about here is really the first step, but I think that we're heading in a really exciting direction, and there's just a lot of great stuff that's possible here with these kinds of approaches. So with that, thank you very much for paying attention to me, particularly over live stream. This is so much harder, I think, from every direction than participating in an in-person conference. But thanks.